Hello everyone, welcome back. In the last video we have been talking about quantum gates, and all of them were, if you notice correctly, that those were 2 by 2 matrices, right? So they were 1 qubit gates. It will act on 1 qubit and it will give you like another vector in that two-dimensional in space, like the qubit space, right? So those were 1 qubit gates, but when you're dealing with algorithms you need to apply some gates that acts on 2 qubits. Like similarly you need AND gates or OR gates which acts on 2 classical bits rather than 1, right? So it is similar, but as you can guess that these will be not 2 by 2 matrix but rather 4 by 4 matrices, right? So let's work out some examples. The first one and the most important one is the C0 gate, okay, or sometimes it is called the CX, controlled NOT gate or controlled X gate. Okay, so what does it do? So let's write out the matrix representation first and then we will understand what it means. All right, so CX is defined by the following. You have 1 1 in this block, you have all the zeros here because it will be a 4 by 4 matrix. You have all the zeros here, and here it will be 0 1 1 0. Okay, so what does it do? You can check that the following property. You can check that let's say that I have a state in 0 0. Okay, so what is the matrix representation of this? If you calculate it explicitly, it will be 1 0 tensor 1 0, and if you calculate it will be 1 and all 3 zeros, right? So if you act on 0 0 with CX, if you explicitly calculate it, it will just be 0 0. Okay, similarly you just do a 4 by 4 matrix multiplication and then you'll see that. Okay, so if you act on CX with 0 1, you will also see that you get a 0 1. Okay, but if you act on CX with 1 0, then you will get a 1 1. If you act on 1 1, you'll get a 1 0. Okay, so you can check it explicitly by taking the matrix representations. So what does it mean? It means that you can see whenever you have a 0 on the first qubit, it does not change the second qubit. But whenever you have a 1 on the first qubit, it changes the second qubit. All right, and change is like a NOT gate, and which is explicitly the X gate we were talking about in the last video. All right, so this is the idea why this is called the control gate, because the first qubit is the control bit and the second one is the target qubit. Okay, so the control qubit is the one that defines that what you have to do. So CX on 0 alpha, which is where first one is the control qubit and second one is the target qubit. So as the control qubit is 0, then the target qubit will not have any problem, so it will just be 0. I mean, it will not change, so it will just be this. And if you have a 1 in the control qubit and you have some alpha here, then your new state will be X on alpha. X is the NOT gate. That is what we were talking about explicitly, right? So but sometimes what can happen is that there can be some ambiguity where which one is the control qubit and which one is the target qubit. So that for that, what we do is that we write it like this: CX12, where the first one is always the control. The first one is the control. This is a notation that we use, and the second one is the target. Okay, so if I write CX21, then my second qubit is my target qubit and the first one is the control qubit. Okay, sorry, I said it wrong. If CX21, then the second qubit is my control and the first one will be my target. Okay, so let's try to understand what happens. So if cx12 acts on 0, 1, then the first one is my control, which is 0, and so the second qubit is my target, and target qubit will not change, so it will just be 0, 1. But what happens if I act with 2, 1 on the same state? Then it will be that the control qubit is my second one, which is 1, so I have to apply an x on the target qubit, and if I apply an x on the first one, then you'll get a 1 here. So your new state will be 1, 1. So you can see that cx21 and cx12 is not the same. They act differently on the same quantum states. All right. So but there are some operations which was not achievable by any Boolean operation classically, but you can show it that quantum mechanically it is possible. So cx 21 can be proved to be equal to Hadamard cross Hadamard. Hadamard is the 2 qubit gate that we introduced in the last video, and you have this cx12 and you have this h cross h. Okay, so this is something very interesting, because by just applying Hadamard gates before and after, you can prove that you can prove that the role of the target and the control qubit swaps. All right, how can you prove this line? You can prove it by explicit matrix representation. That's the brute force way of doing it. All right, and this h cross h means that if you have a 2 qubit system, then you'll apply an h on the first qubit. At the same time, you will apply an h on the second qubit, right? Because h was a 1 qubit gate. All right, so sometimes cx is also called c0 gate. All right, this is the word that we will be using more in the because it is more used in the literature, but it means the same. All right, so sometimes we will call c0 1 2 or something like that. Okay, so it will be whenever I say c0 or cx, it means the same thing. All right, and we can similarly do controlled z gates. So controlled z gate, so what is that? That is nothing but, if you can check explicitly, cz is, oh, I'm writing with red, sorry. So cz can be written as 1 1 here, all the zeros here, and now here it will be the z gate, not the x gate like before. All right, so you can also check that control z gate means that whenever you have a cz 0 and some alpha, it will be 0 alpha because the control qubit is 0, and cz on 1 alpha will be equal to 1, and you have a z gate on alpha. All right, so these are the examples of multiple qubit gates, or precisely 2 qubit gates, and we can show that with these gates we can also form a universal set of gates, but I don't want to go into that details because that is a bit more advanced. But please try to make sure that you understand these gates, and we'll be using these gates throughout the course. All right, so I hope it was clear to you. Thank you so much.